Today's topic is understanding the loose tube design concept. So, go over here. First, this is a RCEP compliant presentation. So this just means that we've met their standards and requirements. And that means that you can earn credit on completion of this webinar. And the continuing education credits will be granted through the rcep.net online system. This does not mean that they endorse any of the content here, but uh, the content does reflect the opinions of the staff and management of NCAB America, for what that's worth. So, purpose statement. Today we're going to talk about the loose tube design concept and things that go along with it, such as EFL. You're going to learn about that in nauseating detail later. And then here are some specific learning objectives. I'm not going to read them out. I'll just pause for 30 seconds or so for you to review them, the things that we want you to learn as part of today's webinar. Okie dokie. So our agenda, we've already done the introduction and course description and learning objectives as well. So now we're going to do the presentation, and I need to watch the time so that we have time for questions and answers after the presentation. I'll stay as long as you guys got questions or something you want to talk about. So don't feel like, as far as I'm concerned, we don't have to be done 100% at the top of the hour. I'll stay longer if there's interest in talking about something. All right, let's get going. So to orient everybody, really the main context today is talking about loose tubes in an aerial application. Because in a non-aerial application, so such as in a duct, a lot of what we're going to talk about is just not as important, and you'll understand why as we go through this. But aerial cables, they have a tough life because they're outside in the air, so they're exposed to the elements 24/7, 365 for their entire operational life. And in general, most users are expecting to get 20 to 25 years of life out of their dielectric, an aerial dielectric cable, such as an ADSS. And if you're using OPGW, most utilities are expecting at least 40 years. I've encountered one utility that wants to get 80 years, and I know of one utility that has put a lot of thought into this matter, and they think that 70 years is very realistic. Of course, the cable has to be well designed and well made. And that's why this whole topic is important, because loose tube design details are critical for getting optical lifespan such as 20 or 40 or 70 years. So during that operational life, environmental conditions are constantly changing. So you've got temperature changes. The ambient temperature will go up and down. And then plus, it could be sunny or not. So the same ambient temperature, the cable will heat up more on a sunny day than if it's a cloudy day. In addition, you've got wind speed changes and snow and ice load changes. So these changes are causing change in tension, and really what we'll see is important from an optical standpoint in elongation of the cable. So how do those changes actually affect the fiber itself? Well, let's look at it. So let's imagine that we made an aerial cable with just one element. So just like a center wire or a center fiberglass rod. Our material doesn't matter at this point, just one element to keep the analysis simple. And we're just going to look at a short unit length of it. So this length will change in response to environmental changes. A lower temperature would cause it to shrink back, and a higher temperature or ice or wind loading would cause the cable to stretch. So these changes are going to happen regardless of the material type, but that doesn't mean the changes are going to be exactly the same regardless of the material type. So in a dielectric cable, meaning fancy word for plastic cable, such as an ADSS cable, relative to a metallic cable, what you would see is that the change in length due to change in temperature is small. Again, relative to a metal cable. Why? Because the thermal coefficient of expansion of the materials used in a dielectric cable is on the order of 10 times less, maybe even more, but on the order of 10 times less that of a metal cable. But because of the nature of plastic materials, the change in length due to loading changes, so wind and ice load, is very large. So plastic cables stretch a lot when they're under load. Metal cables, it's the opposite. So relative to a plastic cable, the change in length due to a change just in temperature is large because its thermal coefficient of expansion is substantially higher than it is for a dielectric cable. And again, relative to the dielectric cable, the change in length due to loading changes is small. So a metal cable doesn't stretch as much relative to a plastic cable in response to wind and ice load changes. Doesn't mean it doesn't change at all. I'm just saying relative. So now let's say we want to add a fiber to our cable. And to keep it simple, we're just going to glue our fiber on the top. You can pick your favorite glue, super glue, gorilla glue, doesn't really matter. We're just going to attach the fiber to the top, and then we're going to see what happens when we change temperature and loading conditions. And what we find is that the same things are going to happen. A lower temperature is going to cause the cable and the fiber to shrink back, and a higher temperature or increased wind or ice loading will cause the cable and the fiber to stretch. But there's an important difference. The fiber has its own material properties, so it has its own thermal coefficient of expansion and its own modulus. So its responses to these changes are going to differ from the cable itself. And specifically, what's going to happen is the fiber is tending to resist the changes. So when the cable is shrinking, the fiber could buckle, perhaps breaking the bond. And when the cable is stretching, the fiber is forced to stretch too. It's trying to resist. And so that could lead it to break itself or break the bond. So if the fiber and the cable are not naturally working together, what does that mean? So how is that going to affect the fiber's operation and its service life? And if the answer here is something that's not good, negative in nature, is can we find a way to add the fiber to our cable while avoiding whatever those negative things are? So let's look at each of these questions. So they're not working together. What happens when the cable is shrinking? We said the fiber could buckle, so that it would look something like this. So the operational effect, so the immediate effect on the fiber could be macro bending. We're going to define this term later, so hold that thought for now. But just for now, understand that macro bending could lead to increased attenuation. So you could see a negative effect immediately. Now, today's fiber, you see bend insensitive fiber, so that would tend to mitigate that a little bit. But still, in theory, you have the possibility of this macro bending leading to an immediate adverse effect on the cable's performance. What about your service life? Well, none. The fiber doesn't like the macro bend, but it doesn't necessarily do any damage to it right away. So what about case two? What about when the cable is stretching? So the operational effect, the immediate effect is likely none. So the fiber is strong, and until the fiber breaks, you don't expect to see, or just before it breaks, you don't see much change in its optical performance. So the attenuation doesn't change. So its ability to transmit light continues until just about the point where it breaks. But the service life is a different story. We're going to see in a moment that there likely could be an adverse effect on the service life of the fiber because of it being under stress. And that's an important point. If the stretching, so the strain exceeds a safe limit, there's likely going to be an adverse effect on service life. So this leads to a couple questions. One is, what's a safe limit? And the second question is, can we quantify how much of an adverse effect we're going to get? And the answer to both of these questions is that Corning has done research that help us answer both of these questions. So let's look at that. Corning's research says if you want, it doesn't literally say this, this is kind of a big picture summary of it. If you want a 40-year service life, you can allow fiber strain up to 0.2%. This is a classic, well-known, long-standing limit within the fiber optic cable world. There's really a couple papers where you can demonstrate this value that go back to, I think the first of these was like early 90s, so a long time now. What if you don't need a 40 life? Well, if you only need a 4-hour life, you can let fiber strain go to 0.33%. And if you only want a life of 1 second, you can go up to 0.5%. Now, these are expected life calculations, which means they're basically a probability and statistic mathematical calculation. This does not guarantee your life. So if you had a fiber under strain of 0.2%, it doesn't mean that every single fiber is guaranteed to last 40 years. It just means the probability is that it will last 40 years. This is based on a low risk of the fiber breaking. And it's roughly this value that you see here, 0.005 breaks per million fiber kilometers per year is what your odds are. And this is deemed an acceptably low number. That means if you know some things about your optical network, you can calculate how many breaks you might have in a year based upon the strain on your cable. Now, the flip side of this is that, again, it's a probability calculation, excuse me. So there's not 100% probability of a break either. Again, this is just the betting odds. And this is Corning's data, but other fiber suppliers have done their own testing and they get similar results. So we had that question, what's the safe limit for the strain? And the answer, quite simply, is if we want 40 years or more, then 0.20% is our safe limit. If you want a lower life, like I mentioned, ADSS, if you're planning on your ADSS lasting 20 years, well, you can go back to this data and you can actually use it to calculate how much strain you could allow in the fiber to get only 20 years as your probable expected life. So, and the second question, can we quantify the degree of adverse effect? Well, yeah, like I just said, you can predict service life, operational life, just based upon the amount of strain that's on the fiber. But you, as users, are buying cable, you're not buying fiber. So you actually have to make another connection, and that is to translate the strain that's on the cable to the strain that's on the fiber. Not going to talk about doing that in detail today, but you understand the concept and it can be done. So you can estimate service life of the fiber on your system, and you can understand how the service life of fiber on your system might have changed due to events. So, for example, if you're in a part of the country and you have a horrible 1 in 1,000 years ice storm, you can actually work with the cable manufacturer to figure out how much strain was on your cable and use that to estimate how much remaining life you might have on your cable. So, but remember, even before we started talking about the effect of strains on the fiber itself, we had this other question that was still out there, and that was if the possible effects of tension or compression on the fiber were negative, could we find a way to add the fiber to our cable and avoid those negative ramifications, whatever they were? And the answer is absolutely yes, we can. How do you do that? Well, it's our webinar topic today. It's the miracle of the loose tube design concept. And in fact, this is points to the heart of the primary benefit of the loose tube design concept. It's that using the loose tube design concept, you can protect your fiber from strain. Let's see how. So let's go back to our simple cable. And again, we're going to add just one fiber, but instead of gluing it to the top of our cable, we're going to put it into a tube in a sinusoidal shape, like you see here, and then we're going to glue the tube to our cable. This is the loose tube design. So now watch what happens when we shrink or stretch the cable now. When we shrink it, the period of this sinusoidal shape shortens and the fibers sort of bunch up. So let's do like they do at an eye exam. Which is better? One, see the shape of the fiber, or two, see how it's shortened? So that's shrinking. Stretching, the fiber period lengthens and the fibers flatten out. So again, one or two. Okay. So how does this help us with our problem? Well, before this is a good point for us to go ahead and define the term macro bending, which came up earlier. And we're going to add another term there too called micro bending. So macro bending is signal loss from too much bending of the fiber itself. So you've exceeded the fiber's minimum bending radius. And what's going on is that total internal reflection stops working. And total internal reflection, we discussed it in our Fiber Optics 101 webinar, but basically the light no longer continues to bounce along the core of the fiber. Instead, some of it leaks out because of the bend. You don't hit the critical angle, and so the fiber doesn't stay within the fiber, it leaks out. And by escaping in that manner, you're effectively causing signal loss. So your optical performance has been decreased. Microbending is caused when two or more fibers cross over each other. Like you see here, the crossover creates a pressure point, and that creates a microscopic indentation, and you get a similar effect, light leakage. So the light's trying to bounce down the fiber and stay within the core, but instead it hits this little bump and that reflects it at an angle where it exits the fiber. It doesn't stay within the fiber. It's no longer contained within the fiber. So again, you get optical signal loss, which is an adverse effect on the performance of your fiber. So microbends, macrobends, and microbends. So now back to our tube. So in the shrinkage situation, so the cable contracting, we would expect a problem only when the temperature gets so low that the shrinkage has caused the fibers to bunch up so much that you're getting macro bending losses. Now, in our cable so far, we only had one fiber. But if we add just one more fiber, then we're adding the possibility of having those crossovers and thereby having microbending problems as well. Now, it turns out that in today's cables, they're designed to operate down to minus 40C, which is also minus 40F, and not have these problems. So you don't have to worry about the cold side too much unless you're in a part of the country like Alaska or a part of the world, also like Alaska, where you can expect temperatures lower than this. But a cable designer can compensate for the lower temperatures. You make some changes in your design and no problem. I've seen cables designed down to at least minus 60 Celsius, no problem. So the bigger concern is going to turn out to be the elongation, because the elongation can lead to stress and strain on the fiber, and we already know that can be bad. You can break the fiber or reduce its expected life. So, but now that we've put the fiber in a sinusoidal shape, we can expect that there's not going to be a problem until the period has been so reduced that the fibers have basically gotten flat. So now, if once the fibers are flat, if you continue to elongate the fiber is directly experiencing the tension that's causing the elongation in the cable itself. So that much elongation is not likely to happen from just temperature changes alone, at least not on planet Earth. There have to be tension changes too, and these can only come from wind and ice loading changes. So we do note, though, that we at least got some protection from our loose tube design just by putting the fibers in a sinusoidal shape. But then this is going to lead to some inferences, and along the way, we're going to need to define a couple more terms. So inference number one, so if the fiber in our loose tube is in a sinusoidal shape, then there must be more fiber in total than there is cable. So the length of the fiber in total must exceed the length of our cable. This can be expressed simply as length of the fiber is greater than the length of the tube. Now, I would have called this extra length of fiber, ELF or ELF, but nobody asked me. So what's accepted as the term is excess fiber length, or EFL. Everybody in the fiber optic cable industry talks about EFL all the time, believe me. Second inference is that if this is true, that the length of fiber is greater than the length of the tube, then the ratio of the two must be greater than 1. And you can actually quantify that. In today's cable manufacturing, you're typically going to see about 0.25 to 0.30% here, meaning that ratio is 1.0025 to 1.003. Now, you can draw some further inferences. If EFL is less than that, it often means a poorly designed or poorly made tube. There are some exceptions. So maybe I should say a lower EFL than this is cause for question. Maybe that's the better way of putting it, because there are some legitimate situations where it might need to be lower. You should also know that in some cases, EFL can be amped up a little bit. So you increase the sinusoidal shape, and that works with some center tube type cable designs, specifically with OPGW, and we'll talk about that later. But in general, the higher the EFL, the better. Inference number 3. So if the fiber does not experience tension until it is flattened out completely and your tube has stretched, that means that your ratio has been dropping. And when it gets to 1, the length of the fiber equals the length of the tube, then what's happened is there's been a gap between when the tension was applied on the cable versus when the fiber began to see it. And we call that gap the zero fiber strain margin. So it's the difference between when the cable experiences strain and when the fibers first begin to experience strain. It's typically expressed as a percent of the rated breaking strength of the cable. You'll also hear the term rated tensile strength. They essentially mean the same thing. They're just different terms. So percent RBS or percent rated tensile strength. Now, UTS is actually a little bit different. I'm used to working with rated breaking strength or rated tensile strength, not UTS, ultimate tensile strength. A little bit different. Anyway, cables will have a different zero fiber strain margin depending upon how they're designed. And we'll give some guidelines later about that because it's a really important value that I think you should know about your cable. Next up, inference number 4. For the cable to have a good sinusoidal shape, the tube has to be big enough. Common sense, right? And as soon as we add more fibers into a tube, there has to be sufficient room for all of them to have their good sinusoidal shape. So from that, we say there's an acceptable maximum fill factor for a given internal size of tube. If you go beyond that, then the tube has been overfilled, and you know that you've done that when you see your zero fiber strain margin drop. And in general, that's not good. You want a high zero fiber strain margin. And the fibers will be susceptible to macro and micro bending, also not good. So there's a certain fill factor that you need to stay within. So now these inferences lead us to some questions. One, we said that typically the EFL is around 0.25%. That doesn't sound like a lot. Really? Is that enough? Can we do better? What happens if we put more than one fiber in a tube, but the sinusoids are not the same? And in today's fiber optic cables, we're routinely using 12 fibers or more in a tube. What happens if we exceed 12? Because we know there's 12 standard colors, but if we need more than 12 fibers in a tube, what then? So let's look at these questions one by one. So is 0.25 EFL enough? And the answer is it depends upon the cable type and the application. So it's okay for a dielectric cable with a center tube when the cable is not experiencing a lot of tension changes, such as cable in a duct. In fact, in general, you don't, for a duct cable, which is not experiencing tension changes, so it's experiencing some temperature changes, but it's a dielectric material, so it doesn't change its length a lot. In general, you don't have to worry about any of this when it comes to a duct cable. I mean, being quite candid here. But it would not be okay for an ADSS cable with a center tube. You would expect too much elongation, causing too much strain on your fiber, leading to optical problems. Just not good for a self-supporting cable. But if you took a duct type cable and you lashed it to an existing messenger cable, yeah, maybe it's okay. And it could be okay for a metallic aerial cable with a center tube, such as what we call a Type C or Type CA cable. But you need to understand the performance limitations, and we'll bring that up later. But let's go back to this question of can we do better? And the answer again is yes, we can. We can strand the tube. So let's look at what happens if we strand the tube. So to understand the effect of stranding, take a look at this picture of a spring. You can immediately understand that the length of the wire that went into making this spring is much greater than the overall length of the spring. And the shape of the wire is called a helix. So you can understand intuitively that if this was a tube and we were stranding it around something in the center, we would have greatly increased our EFL. So in a real cable, we get something that looks like this. So let's say this is a tube and it's been stranded around a center element. So now we have the EFL that results from the helical shape of the stranded tube. And it turns out that mathematically, that's going to be about 2.5% easy. So roughly an order of magnitude of the EFL that we got in just the tube alone. And these two sources work together and thereby boost our zero fiber strain margin of the cable. And so at this point, we could really start talking about the length of the fiber relative to the length of the cable, not just the tube. So the total EFL in our cable would be about 1.025. And this is often referred to as the helix factor of a cable. Now, if you're sharp, and I know you are, you're probably thinking to yourself, hey, wait a minute, 1.025 is just the factor from the stranding of the tube. What about that 0.0025? And you're right. You really should add the two, but the reality is most cable manufacturers, when they're converting optical length to physical length, they're using just the helix factor, considering only the stranding of the tube, not also the EFL within the tube itself. Just a common practice. Is there a downside to it? Not really. The upside is basically you're allowing your EFL in the tube to give you a little bit of a margin for error, for like helps your cable exceed what you've put on your data sheet as its performance specifications. In other words, your real zero fiber strain margin is likely a little bit higher than what you say it is on your data sheet when you make this simplification. So back to our questions. We had the question number 2 was, what happens if we put more than one fiber in a tube and the sinusoids are not the same? Well, you get something like what you see in this picture. So we have a green fiber with a certain period, and we've added a blue fiber that has a longer period. Well, note all of these crossover points. And remember what we said can happen at crossovers of fiber. You can get microbending. So what you want in your fiber optic cable is not this. You want consistent EFL. Each fiber has the same amount. Our blue fiber has less EFL than our green fiber. So you want them to be the same, and you want them to be well coordinated. So you want the two to have the same period and the same phase, right? I could have the same period with the blue fiber, but be out of phase with it. I could be exactly the opposite. And that would again give me crossovers. So I don't want them. So I need the fibers to have the same EFL and be well coordinated with each other. Our third question was, what happened if we needed more than 12 fibers in a tube? And the answer is there are two possibilities. The first one is that I can use ring or band marking, just different terms, the same thing. They both mean I repeat the 12 standard colors with black marks on them in a pattern such as this. The first 12 fibers are the standard colors. Fibers 13 through 24 are the standard colors with one ring mark. Fibers 25 to 36 would be the standard colors with two ring marks. And fibers 37 to 48 would be the standard colors plus three ring marks. Now, some of you will recognize that there is a black fiber amongst the 12 standard colors. Obviously, a black ring mark on a black fiber isn't going to work very well. In theory, what you could do is use a different color, but in the real world, that doesn't work well with the manufacturing process, because then you'd have to either have a second printer just to print yellow or white, something like that. Excuse me. or you'd have to like flush out your printer to change the ink color, and it just doesn't work well. So in theory, you could do that, but what's more commonly done, because it's just more practical, is to leave that fiber uncolored and just add the ring marks to it. And it works well in the field. I've done it literally for 20 years. Nobody's complained. Now, in theory, if you had 60 fibers in a tube, you could just keep doing this, right? To be 49 through 60, and we'll add 4 ring marks, but you know that just doesn't work well in the real world. So this band marking system kind of breaks down above 48 fibers. You know, what if you had 72, or these days you see sometimes tubes even have 144 fibers in it. So it's great up to about 48 fibers. What's your other option? Well, the other option is that you could bundle the fibers into groups of 12 with what's called a bundling, sometimes also called a binding thread. And so you get a pattern that looks like this. Fibers 1 to 12 with a blue bundling thread, fibers 13 to 24 with an orange bundling thread, and then a green bundling thread and a brown, and so on. And this system works well up to 144 fibers. And you can use them together, because the band marking system does give you a good backup in case you lose track of the bundling threads during splice prep. So we've gotten positive feedback from our customers because we do both. So we do this belt and suspenders thing. There is one consideration, though, about using bundling threads. And first, let me though actually show you this. Here's a bundle, fiber bundle, and you see this green bundling thread has been wrapped around it to keep them as a group. Because it's green, you know that these are fibers 25 to 36. And you also, if you look closely, can see that there are double band marks, which goes back to here, 2 ring marks. So again, fibers 25 to 36. But the possible objection to using bundling threads aren't those restricting the fibers to move freely as tension changes on a cable or elongation of the tube is changing? And the answer is that yes, but consider that today's EFL control during tubing yields consistent EFL that's well coordinated. It's what we wanted. So while there is some restriction in movement, the bundles themselves are moving as a unit, and so the system does work well. I've not seen problems in the field with this system, and it does significantly speed up splice prep because it's so much easier to separate the blue bundle from the orange bundle, rather than find, okay, I got to find the blue fiber and put it over here, and then the orange fiber over here, and the green fiber, blue, orange, green, and so forth. And then I got to find the blue with the single ring mark and put it over there, and the orange with the single ring mark, put it over there. The bundling does substantially speed up splice prep. And I don't say that lightly, because if you've attended my webinars, you know I'm not generally very sympathetic to splice techs, but this is one case where I am. So now we've talked about things such as the amount of EFL and the tube fill factor and the lay length of the tubes. Do I need to include all of that in my in my cable specifications? And the answer is no. You can circumvent all those details just by paying attention to the zero fiber strain margin. And we're going to define these terms in a minute, so hold with me. Maximum rated design tension, or MRDT, or MRCL. We're going to define those in a minute. And you ought to require that they be shown on the data sheets too, my humble opinion. So let's define them first. MRCL is maximum rated cable load, and this is the term that's used for the maximum tension an ADS-S cable will experience under the highest wind and ice loading conditions. So what you design the cable to. And that's the term that got picked up in the IEEE 1222 standard. MRDT, it means the same thing. It's just maximum rated design tension, and that was the term that was picked up in the IEEE 1138 standard for OPGW. But you see the definitions are the same. I think MRDT is a better term. It's a little bit more precise. Design tension versus cable load. I mean, cable load, that doesn't necessarily imply you're designing to it. It's just whatever the cable load is. But they mean the same thing. It's the highest tension that you're designing to, whatever your assumed ice and wind load conditions are. Now, Mother Nature might subject your cable to much more than you designed for, but that's not under your control. What is under your control is your assumed design loading conditions and then applying these limits in terms of specifying your cable. So here are some specific recommendations. For zero fiber strain margin, ADS-S ought to have zero strain at everyday conditions. So a no ice, no wind, meaning unloaded condition. Right, so on a typical day, your cable is not experiencing, or the fiber in your cable is not experiencing any strain, any stress or strain. For OPGW, the zero fiber strain needs to vary by design type. So for a center stainless steel tube type, I think you ought to have at least 30%. Now, again, this would give you a situation where at everyday or unloaded conditions, there's no strain on the fiber. Now you could say, well, but we only designed at 20%. 20% would be okay. I'm not going to object to it. The point is that you want there to be no fiber strain under an everyday unloaded condition. Why do I pick 30 though if 20 will do? Well, because your cable, a metal cable, is going to creep over time. And I think that's going to have the effect of lowering the zero fiber strain margin over time. So I would like to have a margin for error. And under the traditional NESC Rule 250B rules, tension could float up that much. I don't see that under real design conditions, but it could. So I think 30 is a better value, but I wouldn't object if you made a conscious choice to make something lower because of what your utility is specifically doing in the field. Aluminum pipe type cable, I think you should go for 50%, but the same caveat, you could choose something lower. Stranded stainless steel loose tube, you should definitely have 80%. It is easy to hit 80% with that type of cable. Regardless of what you pick, you ought to pick something and put it in your spec. That's my recommendation. So as for MRCL, remember that's the term for ADS-S. Best practice would be zero fiber strain at MRCL. So no strain even under fully loaded condition, because no strain means no problems. But that's not always possible. So acceptable alternatives. So you're increasing risk a little bit, but it's not zero is the point here. So I would be okay with 0.2%. Remember, that was our 40-year safe limit in theory. Not too bad. You could go higher because, again, with ADS-S, you're not necessarily wanting 40 years. So 0.3, yeah, okay. Above that, though, I think it's risky. I've seen cables that are obviously designed for about 0.4%. Now, remember, this is only when there are heavy ice and wind loading conditions. So it's not 24/7, 365. It's some subset of that. But also remember how your operational expected life dropped dramatically once strain went above that 0.2% safe limit. So if it were me, I wouldn't let it exceed this, but you can make a risk management case that something higher is in fact okay. But again, regardless of the number you pick, I think you need to pick a number and you need to put it in your specifications. MRDT, just the term that's used for OPGW, same thing. It's going to vary by your design type. Center tubes, I think at 60% because that's the traditional NESC 250B condition. I would say 60%, 0.2% or less. You could make, depending upon what your utility does, you could adjust these numbers. Aluminum pipe type design, I think ideal, it would be 0 at 60%. Again, the traditional NESC 250B limit acceptable 0.2% at 60%. And then stranded stainless steel loose tube type, strain should be 0 at 80%. It's not hard to do in that design type. And that allows you to do the so-called concurrent ice and wind loads and extreme ice loading conditions in 250C or D conditions. Again, not in my mind, you can make a case for different numbers. These are just my general recommendations. Whatever you choose, you ought to choose something and you ought to put that limit in your specifications. So at the beginning, I said we would also talk about what else is available. And here we're at that point. Here's what else is available. The opposite of loose tube is something called tight buffer, where each fiber has its own jacket. You can barely see that here in this picture here, but you've got somewhere in here a blue jacket with a single fiber in it, an orange jacket with a single fiber in it, a green with a single fiber in it. Typically you don't even bother to color the fibers themselves because the jacket serves as the identifying color code. These cables are very flexible and they're very easy to add connectors to each of the individual fibers. But the bad news about them is that the zero fiber strain margin is low to no, meaning a zero fiber strain margin of 0. It's not easy to strand these individual units themselves, so you can't get EFL from stranding, and you don't have EFL in the tube because it's the fiber just directly jacketed. So low to no zero fiber strain margin. So they're great for indoor cables because very flexible, but they're terrible for aerial applications. I just don't think they should be used there. Next up is what's available is ribbon cables. There are 2 versions. The original ribbon cables had stacks of fiber ribbon. So you made a fiber ribbon, you glued, say, 12 fibers together, and then you stacked these 12 fiber groups. So this is a cable with ribbon stack. What's newer is to glue the fibers together, but not 100% like you see here, but it's like it at points. And then that makes them rollable. So the general advantage of ribbon cable is that you get super high fiber density. And the ribbon construction allows for what's called mass fusion splicing. So instead of splicing fibers one at a time, you would splice an entire ribbon or 12 fibers at a time. But you lower the zero fiber strain margin in the rollable version, you still can get some. You have no zero fiber strain margin in the stack version. And you've increased your splice loss, especially with the stack version, and probably for the rollable version as too, depending upon how you do the splice. And in general, the rollable version is hated by splice techs. It just makes it hard to work with. Nevertheless, these cables do have their use, and in data centers, and they're used not in an aerial application, but inside data centers, where you really need that very high fiber density. So they have their place in our fiber optic cable toolkit. And then last up is what's called tight structure, where you strand the fibers around a center element, and you glue them in place to keep them there. This is a much older technology. The idea here was thinking that you could control fiber strain. You would allow it, but you try to kind of control it and a little bit limit it. But the truth is, there's no real good reason for this construction, at least not anymore. You end up with a cable that has low to no zero fiber strain margin again, and these cables have had a lot of field problems over time, meaning broken fibers. You also end up with a low fiber density, and you make splice prep really difficult. So really, this is a defunct design type. But I did run into it as recently as about 2 weeks ago with a customer who still had some of this cable up in the air. So it is around, thought you should at least be aware of it. So we've talked about the why and how of the loose tube design concept, and we've talked about the link between fiber strain and optical service life. We've talked about what zero fiber strain margin is and why it's important, and gave you some guidelines on what you should specify. We've talked about MRCL and MRDT, what they mean, and gave some guidelines of what you should specify. And we talked about those other options that you might want to consider depending upon what your application is. So now we can open it up for questions. So for Bob, this will be your opportunity to get some questions in. Well, I think we'll unmute everybody. Certainly you can type questions in the chat. And
All right,
I'll
Mike.
look for them there.
All right, Mike, I got one for you.
Sure.
So in previous, with a previous cable provider, we had an issue one time of, for lack of a better term, excess fiber squirting out of the buffer tubes. So, when they prepped the fiber and did everything right, everything was good, came back, a year later, and, there was excess fiber in the splice boxes. Does that have anything to do with, a bad job on that EFL or something like that?
Yeah. That's
Without getting into, I don't want to go too deep, but just personal experience.
no, I understand it, and it's a great question. So I could frame it as, is it possible to have too much of a good thing? And if you frame it that way, the answer, of course, is yes. But uh, what you're talking about is something that's called pistoning, and pistoning is sort of its own like mini webinar. I might not be able to talk about for a full hour, but I could talk about it for some time. So the pistoning seems to happen a lot with dielectric cables, and actually I did talk about it in field problems. I'm just debating if I should go find that presentation.
No,
And
don't. I mean, not today. We can have this conversation at another time. Because
yeah, well, here's the 2-minute version of it. You've got a couple possibilities. Remember we talked about stranding the tube, but there's a difference between I can strand the tube at a certain lay length, or I can make that lay length lower, which will increase EFL, or I can make that lay length longer, which as a cable manufacturer makes my productivity go up. Now, you would spot the difference between the two cables if you looked at their zero fiber strain margin. Which cable, though, is more likely to allow the fibers to push out over time? Because remember, our cable is changing length. So sometimes the fibers straighten out, and sometimes because the cable is stretching out, and then the cable shrinks, right? The wind or ice load goes away, the cable shrinks back, and the fibers should bunch back up again. So the sinusoidal shape should go back. Well, why wouldn't it? Well, if I lengthen the lay length of the tube in order to improve my productivity, I would expect that you would get less resistance to the fibers pushing out. Or another way of saying that would be that the cable had less ability to keep the fibers in place. I can build on problems by using dry tubes, because in a dry tube, there's nothing to keep the fibers in place. That's one, in my opinion, one of the reasons I don't like dry tubes, because the gel does something, and that is, it's helping the fibers stay in place and move in conjunction with, or in an integrated fashion with, the tube and the cable itself as the cable changes elongation. But there too, not all things are the same. Maybe I get a batch of gel that's a little bit less viscous than what I normally use, or maybe I intentionally use cheap gel that's not very viscous.
Mm-hmm.
So
Okay.
then there's the tube material itself. So some tube materials are going to be more likely to keep or have a little bit more friction to the fibers pushing out than other materials. So kind of all of these things go into determining if you're going to have the fiber pushing out. So it's not really the EFL that's causing the problem, but it is something else about the cable, how it was designed, and or how it was actually made, that are allowing that to happen.
Okay. I mean, definitely good information today.
Well, good. I'm glad to be useful. So, okay. So we had a question: is the percent difference in tension or the difference in length? And I don't understand the question. Roger, if you could give me a little bit more, Oscar rather, if you give me a little bit more orientation, I'll try to answer the question. Is the percent difference in tension or the difference in length? I'm not sure. And then Tufik, hey, hi Tufik. Do you sometimes use fiber with higher proof test? No. I mean, in theory we could, but just in general, we don't have a need to use the higher proof test cables. But what Tufik I may be alluding to is, if you go back here, sorry, back to the beginning. So Oscar's question kind of came early on. Talking.
Sorry, I was on mute, but you answered my question in your presentation. I appreciate it. Thank you.
Oh, okay, cool. No, cool. Glad to know that. We talked about, dang, I really, here we go. Okay. These values here are based on 100 kpsi proof test fiber. You will actually get slightly different values, not slightly, you'll get different values if you use higher proof test fiber. So for 100 kps fiber, the fiber strain and the fiber stress are about a 1-to-1 ratio. So if you actually go dig out the Corning paper where you find this, it'll actually say fiber stress less than or equal to 0.2% of the proof test. And the proof test is 100 kpsi. So that makes the conversion very easy. But if you use 200 kpsi fiber, yes, you would have different values. But 99.9999% of the fiber that's being processed today by cable manufacturers for general use is using the 100 kpsi fiber. So, okay, other questions? Okay, we're a couple minutes past time, so let me just go back to here. Oops. Just to close out, thanks for attending, first of all. Secondly, you're going to receive a follow-up email. That email is going to have a few things in it. A link where you can get a copy of the presentation, the slides, a link for a survey. So take the survey. And then if you want to get the continuing education credits, there's a link there where you go take a 10-question test, you pass it with 70%, and then you get your credits. So you got those three things. So look for that follow-up email. Please do give us feedback. And if you have suggestions for other topics, please feel free to throw them in as well. And again, appreciate everybody's time and attention today. And last call for any more questions. Don't see anything. So again, thanks. Enjoy the rest of your day.
Thanks, Mike.
You're welcome. Take care.
Thank you.
Thank you, Mike.
Bye-bye.